Okay, let's start. So I sent out the homework a few minutes ago. Just to let you know, it's in the form. It's in the form of a Jupyter notebook-like notebook called Google Colab Notebook. I don't have any of you used Google Colab. You have, okay. Basically, Google Colab is part of Google Docs, basically. So, except your document is a Jupyter notebook capable of running Python, and there is a Linux virtual machine behind it, and you can even tie it to a GPU. So actually, one of the nice thing about Google Colab is you get free access to GPU up to 12 hours. In any case, you don't need GPU for this assignment, but it's basically a notebook. Make a copy and just fill it out. The reason I made it a notebook is because a couple of places you'll have to write Python code, so it's easier done that way. And then when you submit, you dump a PDF and upload that to Gradescope. And in one of the places at the very top, I ask for the URL of your copy of the notebook so that I can go there and run your code. So yeah, it's pretty straightforward. So also, any questions about the presentation logistics for Monday? We'll again, I'll send out, I'll create a Gradescope submission thing half an hour before the final exam. Just upload your PDFs so that I can have all of them on my laptop. Otherwise, very similar in style to the checkpoint presentation we had a couple of weeks ago. Okay, and yeah, the final thing, everything else is due next week, Friday. So last lecture we talked about that how the process of sampling or making measurements can be made more parsimonious, so that instead of sampling by the Nyquist Shannon-Nyquist rate, you can approach it from a couple of different directions. One is that we know more about the signal, and therefore we could be smarter about acquiring the information. So in Shannon-Nyquist, we basically assume that the only thing we know is the bandwidth, whereas if we know more, and the example I had was, what if we knew it was a sine wave, then we know sine wave only needs 3 parameters, so I could kind of start from that. And more generally, what compressive sensing literature makes use of the fact is that we know, we may know that the signal is sparse in some domain, and by sparse in some domain, I mean if you were to project the signal from the time domain or space domain into one of those domains where you know it is sparse, then the number of coefficients in that other domain are going to be mostly zeros, and so you use that in your optimization. So for example, we may know that, hey, it's sparse in frequency domain because maybe it has a small number of resonant frequencies at which it works, or if you don't know what domain it is sparse in, then it turns out that actually just doing random projections works nicely. So the idea then is that instead of sampling according to Nyquist rate, we take a bunch of samples, we collect a bunch of random sample vectors. So you can think of that process itself essentially as a linear operator. So in this case, I had a signal, I kind of was taking some samples, and you can think of that as multiplying the original signal, the original vector x, by a matrix where ones represent that I'm taking a sample and 0 means I'm dropping the sample. So this would be some reasonably sparse matrix, which we do that. Then the other thing, that if we know that we are sparse in some domain, so let's say we know that x, when projected into FFT domain, is sparse, then we can say that I can go, I can again do a linear transformation of x into y. So y is some psi times x, and that we know results in a sparse signal. And then we formulate the problem as that we know z is the sampling matrix times x, y is the transform which makes it sparse. So we can write z as in this manner, and then the whole problem boils down to that we want to find a y hat such that the sparsity requirement is met. So y hat is that y tilde which meets the L0 norm requirement, namely saying that most coefficient that we want to minimize the number of non-zero coefficients. It is this optimization problem, and the key insight and the proofs and all behind this were kind of two main things. One is that this problem can be solved by doing an L1 minimization, which is very efficient. So L1 minimization, L1 norm basically is that the magnitude of the largest coefficient is minimized, and the other thing is that even if I don't know this, even if I don't know the domain in which it is sparse in, it turns out that random projections work pretty well in recovering these things. So compressive sampling has very close ties with a whole bunch of other concepts that exist also. So compressive sampling also has close ties with an area called sketches in computer science. A sketch, as the name implies, is I give you something and a sketch is kind of like a rough diagram of that. So it turns out that in many places where you have large amounts of data coming in, data streams coming in from sensors or network traffic and whatnot, and you want to compute some statistics over it. So let's say you want to compute a median or some 75th percentile or something like that. So sketches are a way of sampling the stream such that I can compute the statistic of interest very efficiently without keeping all the samples with me. Okay, so there's a whole rich literature, and it turns out that compressive sampling and sketches, these were developed around the same time, and they are actually kind of deep down equivalent. So this this notion is sort of tremendously useful. When it comes to minimizing the measurement, there are many different settings in which it becomes beneficial. So first is that every time you collect a sample, there is an energy cost incurred in this thing, right? You have to amplify the signal, your A to D converter has to do a sample and hold and digitization and all. So you can save there. Even if your A to D converter and all are cheap, if your sensor is a dumb sensor and it's going to send the data across, then it is going to consume bandwidth over the wireless link or the bus in your node. So again, doing compressive sampling, and as you can see, compressive sampling in this case is nothing but some random matrix that can be tremendously beneficial in reducing the bandwidth. Also, if you have less data, then you have to process less. And then finally, one nice thing about compressive sampling as opposed to sample fully and then compress as we normally do, we capture the image and then do a JPEG compression in the camera. The advantage of this kind of approach is that the heavy burden is all on the receive side. So the sending side is basically doing this kind of randomized sampling, which is kind of super efficient, as you might imagine. The receive side is doing this optimization problem, whereas things like JPEG compression and all, they are kind of designed to be more symmetric. Both sides kind of pick up the equal, somewhat equal burden. So lots of nice characteristics. Anytime taking a sample is expensive, or sending samples is expensive, or the sensor is very resource constrained, this kind of approach is useful. And like I said, there are other mathematical equivalents. After all this work came out and all, there were, then as is often the case, they found that some prior work out of Russia, for example, had anticipated these kind of ideas, and also then in pure math, some of these ideas had been floating around, but in signal processing and all, they kind of became known only relatively recently. Now, that's not the only way. So compressive sampling has the makes the statement that if you tell me more about the signal, I can be smarter about it. But there are other ways to also optimize sampling. Another direction you can take is, if you tell me more about how you are going to use the signal, then I could be smarter about it, right? So if I know that you don't seek to reconstruct the signal, but perhaps you only wish to compute some specific function of it, like in my sine wave example, what if I tell you, hey, I only care about the frequency, I don't care about the phase and the amplitude, then maybe you can do even smarter. One context in which this kind of question gets asked is if I'm using the sensor to control something, and which is almost always the case, right? I mean, we sense something to then make some decision and then try to keep an overall system in some sane state. So some work has kind of looked at that, so that's what I'm going to touch upon. And the intuition behind this is the following. Another intuitive way you can think about being smart about sampling is the following. If the signal isn't changing much, then perhaps I shouldn't do anything. So if you go back to your control courses and all, typically what happens is we have a set point, and then we kind of look at the output of the sensor and we see that, hey, you know, I'm moving too far away from the set point, so we adjust the command to the actuator, move the motor one way or the other, or apply some force. So that's kind of the intuition out here. So taking that as an example, let's imagine we have a motor controller. The motor is equipped with some sort of a position encoder, which is sensing the motor's position, and then and the set point is basically the command. So we say motor should be in a particular location, and then we take the motor controller internally, takes the delta between the set point and the position encoder, and then based upon that computes how much voltage or current or whatever to apply. So traditionally, these kind of systems are again sort of done in a uniformly sampled manner. That is, this sensor is going to take a sample every time period, and the whole thing kind of runs in a synchronous manner. Every clock tick, we are taking a sensor sample, comparing it against the set point. Set point may change, but perhaps slowly. Usually, these control algorithms are things like PID control or PI control or something like that, and nowadays kind of more sophisticated model predictive control or even machine learning algorithms of various forms, or like what Sandeep described, the reinforcement learning type stuff. But that's normally what kind of goes on. So what happens in this setting is that every sample that we collect has to be digitized, as most systems are currently digital, and then needs to be processed. So now, as you might imagine, even if the motor is perfectly stable, it is sitting at that set point and there's not any perturbation happening and all, we are still kind of chugging along. We are still kind of sampling and processing and whatnot. And oftentimes, this kind of situation happens that I'm trying to control something and everything is steady state, nice and all, and yet our whole system kind of operates in this manner. So this is where we can bring to bear our intuition that if things aren't changing, then I can increase my sampling period. Basically, I can reduce my sampling frequency. So that's the idea, and this work actually, this stuff was done by Professor Pallet out here. So it's a very famous paper of his. So kind of the notion that becomes is that instead of sampling kind of in a regular manner, what we do is we change the sample period depending upon how the signal is changing. So in a standard sampling paradigm, every clock tick we are sampling, even though there are times at which the signal is changing more rapidly and there are times at which the signal is reasonably kind of stationary. Whereas this kind of sampling, or the best way sampling, it basically adapts according to that. Now the challenge out here is the following, that we don't know in advance how the signal is going to change, right? Because we can't go back in time. If it was space, this would have been straightforward. I can take a step, my robot is moving around, making samples. If it messes up, it can kind of go back and do a finer sampling. So there has been work again around 10, 12 years ago on sampling using robots, where what they would do is they will first do a rapid scan of the whole area in very coarse terms, and then they will see which areas were exhibiting more variation, and they'll have the robot go back there and do a finer grained sampling, and so on and so forth. So you kind of focus your sampling. If you think of number of samples you can take as kind of like a budget, then you focus the sampling on those portions where there is more change happening. We want to accomplish the same thing in time, except in time we can't kind of go back, so we need to do something else about it. So so the key question then becomes, how do we decide this interval? When should I collect the next sample? So the idea that Professor Tabuada's work had is called event-triggered sample. And in an idealized sense, the notion that they have is the following. Before the A to D converter, imagine there is some sort of little circuit sitting, and it is monitoring the analog signal. And what it is going to do is, it is monitoring this analog signal, and if the analog signal has changed enough, then it will ask the A to D converter to trigger, and then a sample is produced. Now, so essentially it's saying, I want to monitor the analog position waveform, and if the position has changed sufficiently, then I'm going to have to digitize it, and then the control algorithm will process it. Do you see a problem with this? Okay, that's one question. How much is enough? Let's say we provide the answer to that. Do you see some other problem? Where is all of this stuff happening? On the analog side, right? So somehow on the analog side, I have to do all this logic about, has the signal changed enough and all. And remember, if I'm on the analog side, I can't do sophisticated things, right? I mean, I have to compute whether the new value, okay, firstly, obviously I'm not allowed to digitize, because if I go to digitize, then I might as well have digitized to begin with, so I shouldn't be digitizing. So if I purely want to do on the analog side, then I need to perform potentially some complicated expression on the analog side, and then trigger the A to D converter based upon that. So that's one way we could do it. But let's say we pull it off. Let's say we are able to design such an analog circuit. Then, in essence, my A to D converter is no more being triggered by regular clock, but instead my clock is this data-driven clock, right? It's continually monitoring stuff. So in that famous paper of Professor Tabuada, what they did was for a control system, they showed that that is Swapnil's question, that what that bound is. So they basically found the criterion where it basically says that the current value of the analog signal minus the previous sample that we had collected exceeds some sigma, some constant, multiplied by the current value of the signal, then the control loop remains stable. Okay, so in control theory, you basically worry about the stability or the convergence and stability properties. So sigma is a design parameter which basically trades off performance against the sampling rate. And kind of intuitively what's going on is we are basically saying, if things have not changed much since we, if things have changed sufficiently from the last sample, then go ahead and sample. That's basically all that's going on out here. But the implementation challenge here is, if you don't do anything else, the implementation challenge here is that I need to do all of this thing in analog, which includes taking absolute values and stuff like that, and these things are kind of a little bit tricky. So whatever gain you may have in saving on the samples may be frittered away in the power that this guy is going to consume, and this guy is going to consume all the time. So actually in my group, when this paper had come out, we had kind of tried it out for some ECG monitoring and all, and turned out it's kind of pretty painful to do it on the analog side, so then didn't really kind of work. So pure event triggered doesn't work very well. So then there is an approximation of that, which go ahead.
If it's below the threshold value that you're setting, you're multiplying the current.
If it has changed enough, then you are going to
Sample again?
sample again.
If not, you just like kick away.
If not, then the HUD converter will not fire, but you are still monitoring this. Right? So you're still so you're always monitoring. So in this idealized thing, you are always monitoring on the analog side, and the moment the signal has changed enough, you are going to collect a sample.
But you were saying it's better to have it on the digital side?
Well, what I'm saying is the following: that doing this requires continually solving this equation, which means you need an analog circuit which can do subtraction. That's D3. This is not N, but you also need to do a absolute function, and then you can do a comparison. Comparison is again easy, but you're going to have some circuit sitting there burning power all the time. So if your goal behind all of this was to save power, then whatever you are saving on sample collection, you are kind of losing it away on a more complicated analog circuitry. But remember, I said another use of this thing is to save on bandwidth, right? So that leads to kind of the other notion that they developed, which is kind of an approximation. So the problem is that the event controller, the one which I previously described, has to check for that inequality at all the time. We don't want to do that. So instead, the approach is the following. When we design the motor controller, then usually the way these control algorithms are developed is we'll have some model of the motor, and then the controller is designed with that model in mind. If you're designing, let's say, a control algorithm for a drone, then again you'll have a model of kinematics and dynamics of the drone, and then you design the controller based upon that. So we know in these problems we have the model of whatever our physical plant is. So then the idea is that given the current state of the motor and the command that we have, we can get an estimate of the next state. So the idea is that instead of relying on the sensor to tell me what the next state of the system is, I have a model of the system, so I can go one time step open loop. I can predict where the motor ought to be given the current command that I have given. And then based upon that, I can decide whether I should sample or not. So we kind of tolerate some error where we're basically saying instead of monitoring the sensor all the time, let's just predict based upon my current state and the model of the motor that I have as to where the motor would be one time step from now. Would it have moved enough? And if so, then I'm going to go ahead and sample it. So we kind of switch into a predictive mode. So we basically predict one sample ahead and then say, look, what things change sufficiently, so let's just go ahead and sample it. So in this case, we are instead of we are taking the current measurement, or I guess you can say the most recent measurement, plus the system dynamics, and from that we try to say what is the good time to collect the next sample. Now, of course, there's a probability you might go wrong, and also so you are trading off kind of a simpler implementation. Essentially, we can do all of this on the digital side. We don't need that analog circuitry, but the penalty is that may not work as well, because whatever model you may have, the reality will always differ from it somewhat. So there is a modeling error that creeps in, and which means that you'll have to provide some guard band to protect against this. So that's the idea behind this whole self-triggered control. I'm going to skip this slide. Okay, so these guys kind of applied it to a variety of systems and all, but I mean, shorn of its mathematics and all which exist in the paper, the intuitive idea basically really kind of boils down to is that in control systems, I can basically there is a condition that exists which basically says if the signal has changed sufficient, and by signal we mean the state of the physical plant has changed sufficient, then we should go ahead and kind of update things. And there is an approximation of that you can easily do on the digital side, which requires that you should have a model of the plant. Now, I guess the philosophical question you can ask is the following: if I have a model of the plant, why do we do controls? Why do we do that? Why don't we go open loop? Like if I have a model of whatever I'm trying to control, then why do I need a control system? Uncertainties, right? More, not just there's modeling uncertainty, and there is also noise and perturbations and stuff like that, right? So, so that's why we do feedback control. But when we do feedback control, still to design a good controller, we always kind of start with some model of the system and work off that. Oftentimes we don't. Oftentimes we kind of say, like a lot of practice, I'm told, in control systems is they use PID controller, and then they kind of experimentally find out what the PID values are, okay, and not go through much deep effort, and likewise kind of experimentally determine the sampling rate and all. So there is practice, and then there is theory, and I guess they kind of meet somewhere in the middle. Okay, in any case, to summarize then this whole sampling story, in recent decade or so, a lot of effort has gone towards making sampling more efficient. And the reason partly being that in many settings we care about the energy spent, in many cases we care about the bandwidth spent, in many cases we have a very expensive sensor, so if you can reduce the number of sensing elements that I need, all of those are potential sort of benefits. And kind of the key idea behind these things is kind of really exploiting two different dimensions. One is that we know more about the signal, so essentially it's kind of like know your data, or know the process which is generating the data. If you know that, then you can be smarter about sampling. In fact, you can be smarter also about machine learning and all sort of stuff. I mean, when you start on a machine learning task, they often say the first thing you should do is to really understand the data, right? So that you know what features to use and stuff like that. So it's the same story out here. If I know how the process, how the underlying physical process, what the physics of it are, so that what's the shape of the data, if you may, then I can exploit that for sampling. So that's one. And the second thing is that reconstruction is not always the goal. In fact, it's almost never the goal. Reconstruction is only useful for visualizing stuff. Usually you're trying to do something concrete, control a system, draw some particular inference, something like that. And so again, that's something that we can make use of to result in better, smarter sampling. Okay, so so that's the story on sampling. Sometimes it's called compressive sampling, sometimes it's called compressive sensing. It's kind of all the same terms. Okay, and sketches, if you hear that, that's basically the same thing, just coming from a different side.
Are they expecting kind of like combine the two models, so like if you're like not fully using the state estimation?
Yeah, they have. So it's what I have shown you is like 1% of what exists in this field. Okay, there are immensely deep theories, and as well as lots of hardware advances. Like just like we have A to D converter, there is analog to information converter. So a lot of work at Caltech along those directions. So a lot of optimized hardware also has emerged. Also doing computation while remaining in the compressed domain, so that you don't even decompress, you just do the computation on the compressed data. So all those stuff exists. Yeah. Okay, so next thing wanted to cover is how do we go around making inferences from the data that you have collected. So kind of at a philosophical level, our systems tend to have two broad categories of sensors. This is a term from robotics. One are called as proprioceptive sensors, which basically means sensors which are about ourselves, so they're looking inwards. And they are, so in case of a robot, it could be temperature of the motor, for example. Exteroceptive sensors are sensors which a system has to look outside, like a camera looking outside for obstacles and stuff like that. Hearing sound outside and all. And if you think about it, our human body, again, I mean, normally we think in terms of those 5-6 senses that we have: touch, sight, hearing, and all. But we also have a lot of other sensors, like our sense of balance, a sense of pain. Those are all examples of proprioceptive sensors. So we tend to have both, and then from that we try to kind of make sense of the world. So one thing that a lot of people say is that a key to intelligence. So firstly, if you recall, I had that slide last time showing kind of this whole loop: perception, comprehension, projection, decision, action, and we kind of go along that. But in the same vein, a lot of people also say that the key to intelligence is our ability to have a model of the world. And then when we make a decision, we really make a decision with respect to that model, right? So all these sensors and all, what they really do is they help us help the system develop a notion of what the state of the world is, and then whatever action and all we have to take, including when to sample next, right? Where to sample next. All of these things are with respect to that model of the world. Now, before we get to that, though, one of the challenges that we also face is that these sensors are almost always bad, okay, in the sense that they suffer from noise and calibration and all sort of issues. So our brain actually tends to be pretty good at compensating for them, right? I mean, after an initial period of adjustment, we kind of adapt to a misaligned something, okay, or people even adapt to, like, after let's say damage to some of their perception capabilities and all. So in this process, the thing to keep in mind is that the sensor measurement is not the same as the state of the world. And what I mean by that is that when we are seeking to measure something about the world, like where are the objects in this room, things like that, the sensors are not directly telling us that information. So they're not giving the state that we are interested in, but rather they're telling us something about the state. So they may tell some physical things like light level and color and blah blah blah, and then somehow we kind of go from those measurements into the state of interest. So one thing that we immediately face in this thing is that the same physical quantity may be measured by multiple different types of sensors. So that's one thing. And the other thing is the same state of interest, like the position of something, like position of a particular individual in this room, that could be measured in a variety of different ways. So there is this sort of gap, and we can bridge it many different ways. And one thing that sort of we see in recent years quite a bit is that as our ability to process data and detect patterns in it and other information about the world advances, then we can often make use of sensors which we might not even imagine can sense something. So to give you one example, the accelerometers, which are built into our phones and many of you are using in the projects, they can pick up sound. And the reason they pick up sound is because they are basically little MEMS sensors. They are basically a free sort of mechanical thing suspended in a chip, and so it basically measures vibrations. So when there are air pressure waves, they kind of move that object around, and that's what the signal picks up. So people have shown quite a bit that gyros and accelerometers in your phone, they pick up sound to the extent that you can certainly make inferences about the acoustic environment, is the person speaking male or female, or those kind of things? Is someone speaking? Is there an explosion? Those kind of things. But also in many cases, even to a level where you can detect words or even reconstruct speech. So that exists. Almost anything with can be, well, let me rephrase. The world is so complicated that almost every sensor picks something about any phenomenon of interest that we might have. So let me ask you simple as a thought exercise. You know how in your phones you have that battery level indicator, right? I mean, it tells you the current battery level of the phone. Usually information about the battery level of the phone is unprotected information, so any application can access it. If I were to assert that an application which is connected to the internet, so has access to information which is out there on the internet, readily available, and reads the battery level on your phone, that it can therefore figure out what your position is. How do you think it? Can you think of a way that we can do that? So from the battery level, let me kind of rephrase this, not from a single measurement. So it's just taking a series of battery level measurements. Okay, can you think of some plausible way we can find the location track of your phone from that?
If you do like a general prediction of where you are at a given time of day.
Yeah, exactly. I mean, I want you to I want the app is basically interested in knowing where all you are going. Okay, so and again, it has access to readily available public sourced information. Okay, kind of the information out there, and it has from your device. The only thing it takes is not your GPS readings, not your inertial sensors, not sound, anything. The battery level. Anyone wants to take a stab? So is there anything on your phone whose power relates to location? Huh? You said GPS, you said IMU's power consumption is reasonably stable. So it's not, GPS power consumption is reasonably stable. Cell connection strength. Okay, great. So cell connection strength relates to distance. Can you think of a way to now map it to a location? And remember, key thing is you know other stuff about the world. Right. So cell tower locations are public, almost public, since they are readily available. Map information is public. So by knowing the change in power consumption relative to cell towers, you can see how you are moving. You can seek to fit, if you are moving at vehicular speeds or pedestrian speeds and all, you can begin to fit it into the maps and then work your way into where you were, because once you have a unique pattern, you can fit it into after a reasonably sufficiently long trace. Okay, you can then fit it into the map and figure it out. So the reason I mentioned this was because this was a paper a couple of years ago out of a group at Stanford which did precisely this. Okay, they basically based upon this kind of figured out where you were. Around that time, one of my students, we did a similar work, and which was along the following line. So your phones have barometers, right? Or rather, barometers, so air pressure. They're publicly accessed, or at least at that time they were publicly accessible. We converted that into a location trace, and the way we did that was the following. Since these are pretty sensitive barometers, so they can even measure things to around a meter type sensitivity. So we basically collected the profiles in the change in height. Remember, we don't have access to XY, but we have access to the change in Z. And if you are living in a terrain where, I'm not in middle of the country with flat land, but like, let's say here with sort of hills and stuff like that and all, then again we can fit the profile to a topological map. And indeed, that's what we did. So essentially, immense amount of data, namely mapping information, and immense amount of computing, namely doing all this optimization and search, can lead to sort of breaking things. So I guess all of this was a digression to kind of really make a point that you should think about sensing in a not in a very narrow sense, but rather the state of interest to you is often gleaned from tidbits of information which you are gathering, and then together with side information. So all this stuff like maps and all is what is termed as side information. There's a term for it which someone who used to be a professor out here, she calls it as small data. So instead of big data, this is really small data, like teeny bits of data stitched together into kind of complicated inferences. Just wanted to show you that how even something as simple as measuring distance to an object, there are many different ways you can go around doing it. You can do ultrasound time of flight, infrared with signal intensity. You can have stereo cameras. You can have a single camera, but make use of motion or make use of some assumptions about the size of things, right? I mean, we know roughly what physical objects look like, and also we can make use of that prior information. We can use a laser plus a fixed camera. We can use LiDARs and stuff like that. There are a whole bunch of things you might imagine that can be done around this. Likewise, if the task is to detect people, you can imagine a whole bunch of ways doing it. And I guess some sensors are more easily able to detect a range of things, like cameras have a lot of things, but on the other hand, oftentimes even very simple sensors glued with kind of sufficiently rich side information can do a lot of cool stuff. Okay, so one area which of quite a bit of interest in across a range of applications is what is broadly referred to as detecting activities and behaviors and things like that. So if you think about us humans and systems that are trying to sense about us, which is pretty much everything, advertisement companies and to medical research and everything, okay, they're kind of different aspects of the human state that are of interest. Certainly our physiological state, whatever health conditions and all, our activity state, like how we are moving and stuff like that, our mental state, like are we depressed or happy or stuff like that. All of those things sort of fall under kind of this category of work. And if you think about like how we can go around sensing these things, one way is to put sensors on in the environment around us, detecting these things. So many of them exist, right? I mean, PIR sensors, so those are those little motion sensors. Every time you open close a door, just that. So magnetic door window sensor, or even sound based thing, right? I mean, that door just shut and there was a sound and with a very unique signature. Vibrations. So every event which takes place in the physical world has kind of a multispectral signature that can be picked up. Could have certainly used a camera, could have used microphone, as I already said, and so on and so forth. In fact, to an extent that there is a rich body of work around kind of many of these sensors trying to make a rich sense of things. Some of these sensors are very local, like they just tell us, like if there's a magnetic door window sensor, it's basically telling us about that particular door or window, not much else. Its footprint is very small. On the other hand, something like let's say camera has a bigger coverage, but of course is obscured by walls. Things like electric meter and water meter kind of give us a whole house type thing. And by bringing right models, right type of site information and processing, we can disaggregate these things into what might be happening at different places in the household. So for example, electric meter, there is a whole body of work which is referred to as non-intrusive load monitoring. And kind of the idea is that any time any electrical stuff runs in your home, then it leaves an imprint on the AC lines in a couple of ways. One is these things consume power. So there would be some signature on the current waveform, which the meter is measuring. So the meter, the moment you turn your TV on or off, there is kind of signature coming there. The other thing is that many of these devices, when they turn on off, they cause a transient in the voltage, right? I mean, I'm sure you would have seen these things, like a heavy duty load starts, and kind of the voltage may dip a little bit and all even. But even if it doesn't, you will see signatures. Your laptop power supplies, for example, these are so-called switching mode power supplies. So every time you connect your laptop to the outlet, there is a back injection of some AC frequencies. So if you monitor kind of the wideband spectrum on the voltage line of your home, you would see kind of a rich array of signatures there, to the extent that you can identify that there is an Apple laptop there or stuff like that. Water meter has a similar thing, right? Every tap or faucet or water egress device has a unique signature. When your washing machine runs, the way it sucks the water out is very different than, let's say, when you're taking a shower or when you're washing hands. So the point being that some of these things may sound pretty innocuous, but given sufficient models and all, you can learn quite a lot about the activities taking place inside the household. Okay, the other type of sensors are sensors on ourselves. So certainly inertial sensors, but we are increasingly seeing a whole bunch of other type of sensors that exist, particularly in watches, a whole bunch of health-related sensors and all, which have begin to emerge. So we have both of these things, and then the more general problem then is that how do we stitch all of these together to get kind of the information about human activity that we are interested in. And the trade-offs in these things are often about cost, availability, the accuracy and stuff like that. So advantage of the stuff in the environment is that they're always, once instrumented, they will work for any individual who enters into the place. The flip side, though, is that it's pretty costly to equip the entire world with these things. The sensors on the body are always there with us. So if the primary goal is to monitor a specific individual or a specific group of individuals, then this is a very cheap way. You can always kind of do it. On the other hand, it often lacks perspective because it is seeing outwards. It's not seeing at us from outside. So certain activities and all become kind of harder to do it this way. So more generally, you kind of need both. So a lot of work in kind of broad umbrella of smart environment and all kind of focuses on combining ambient sensors with sort of variable sensors. And then what they do is different kind of activities and all, they kind of look for signatures which manifest across these multiple sensors. And I think kind of probably the one way of thinking about these is make use of whatever sensors are available, because it's very hard to have one solution which everyone would adopt and kind of work with. So this is out of some work at Washington State University at Pullman, Washington. So they have a bunch of apartments in their city which are equipped with these things. They are meant for sort of old people who are on kind of assistive living kind of setting and all. So they are, it's a project called CASA, C-A-S-A. So they have lots of data sets and all that they have published. So this is an example of like hand washing activity. So what you see out here are different, so these are accelerometer, gyro, yeah, the 2-axis accelerometer, gyro. They're kind of picking stuff up, and then here you have motion sensors. And I don't know what P stands for, but a bunch of ambient sensors which are sort of picking this data up. And the challenge we have is that faced with this, you want to really kind of figure out what is happening. So one thing which happens in sensory data often is that unlike images and natural language text or even human speech, it's very hard for us to go back and label these things. So, like for example, if I were to not tell you anything about this is hand washing or whatnot, looking at these, it's pretty hard for us to tell what it is. So, so usually in these systems, what they do is they also put cameras to kind of capture the ground truth, so that you can go ahead and do your modeling and all. Now, of course, that's not a sustainable solution, but the idea is once you do it, then hopefully it generalizes to other population. This is sweeping with a vacuum cleaner. And so what you probably see out here, again, gyros and accelerometers being picked up, but you also see a lot of activity on the sound sensors, for example, out here. So the sound of sweeping coming in. Okay, so how do we formalize these things? So the way to think about the sensing task is the following. So in a sense, my world of interest, the world out there, if you think of that world as having a state, then over time it is moving from state to state to state. So like in that notional apartment, someone washing the hand and was sweeping and stuff like that. So you can think of those as the states. And our sensors are observing those states by virtue of the fact that when the world is in that state, it is emitting signals, and our sensors are picking up those signals. So we don't have a sensor which directly tells us the state, but rather we have sensors which tell something about that state. Okay, and moreover, they tell with different degrees of accuracy and stuff like that. So we can think of our system in this manner, that there is some state which is what we are interested in, which is what we call as inference. So when we say someone is sitting or the head is in a particular direction and all, those are really an appropriately defined state vector. And our sensors are really giving us an observation, which the sensor would give hopefully different observations there, and it will have a noisy, probabilistic kind of behavior. And then on top of this basic structure, you can think of different kind of tasks that we do. So there are 4 very common problems that are solved on top of this. So the first problem is called that of filtering. And basically filtering says that I want you to tell me the state at time t given observations from until time t. So the history and until time t. So that's called filtering. So when you hear terms like Kalman filtering and all, that's really the problem, or particle filtering. That's the problem that they're trying to solve. Given the history, tell me the current state of the system, or current state of interest. Where is the missile coming in, or where is the car? Those kind of things. Then there is prediction. Prediction basically says that given given the state until time t, given the observations until time t, I want to predict the state at a future instant of time. Okay, not at time t, but at some t prime which is greater than t. And this obviously is often what we want, because we want to take an action which itself will require some time, and therefore I need to predict, right? So if I'm going to shoot a gun at the incoming missile, I want to know the position of the missile at the time my bullet will, or whatever, my anti-missile missile will reach there, right? So that's what we want to do. By the way, a special case of filtering is when given the observation at the current time, I'm predicting the state at the current time. So as you can see, normally what we think of inference, and which I think most projects end up doing, is really kind of a special case of a broader problem. Namely, I have the history, and then I have history of observations, and then I am trying to do this. Third one is smoothing. Smoothing basically says that I want to estimate the state at some t prime, which lies in the window 0 to t. Okay, so in effect, it's kind of saying, look at the past and the future, and then tell me a good estimate of that state. And then there is the problem of most likely explanation, which is basically saying that given a sequence of observation, tell me what was the most likely sequence of state that was taken. So in this case, I'm kind of looking at the whole trajectory. So I kind of give you the observation, maybe I collected it through my app, and then later on the advertiser wants to know what all places you went to, right? So I'm kind of trying to come up with the whole trajectory. And then you, again, for each one of these, you can think of cases. So there are certain simplifications that get made in these things. So one common simplification, one common set of is windowing and feature vectors. So we divide the sensors measurements into windows of time, and then we compute a feature vector over that window of time. So essentially, instead of dealing with observations at a very fine time granularity, and instead of dealing with the raw observations, we begin to deal with these feature vectors, which are computed over longer snippets of time. So we both have a reduction in rate and a reduction in the raw number of samples. So you can think of this really part dealing with reducing the amount of data, making use of the fact that perhaps I know that the world doesn't change very rapidly, there is enough stationarity, but also in some cases pesky little issues like the one which some of you faced, which is the samples on the phone are not coming in a regular manner, but there are some samples at some somewhat random time instance. So by putting things over a feature vector and then looking at a set of putting the samples in over a window and looking at features which are independent of the precise location of those samples, then you sort of come out ahead. So essentially, we change these observations to a sequence of feature vectors, and we use that instead. Another simplification that is often used is independence of windows. It basically says that feature vectors are independent, and so we can make independent inferences. So it basically says that this problem, S of t given observation 0 through t, is the same as S of t given O of t. And a lot of people kind of just end up solving that. Under what settings is that a reasonable assumption is I would argue that almost never. Okay, so like for example, let's take something very simple. Let's say we try to figure out, given the current readings, am I sitting? Okay, well, you can certainly kind of develop a classifier and do it, but the reality is that your classifier is going to have some error rate, and occasionally maybe it declares I'm sitting when maybe I'm just crouching or something like that. I'm not actually sitting on anything, maybe kind of crouching prior to a run or something like that. Okay, so what filtering lets you do is it lets you take the context into account. It can say that, couldn't be sitting because the prior history suggests that. So two sources of information are very useful in kind of increasing resilience. One is information from other sensors. Like for example, if you knew that I'm in the middle of a soccer, bad example. Let's say the system is declaring I'm sleeping, but I'm in the middle of a day outside on the road, highly unlikely. So other sensors can sort of compensate. And the other thing is, what was I doing recently? Is this a blip? Is this an outlier? Or is this something that was actually happening? So again, by incorporating prior information, you can actually have a more robust inference. But nevertheless, these two inferences are very commonly used. The third thing to remember is there are two broad categories of problems. There are problems which are classification problems, and there are problems which are regression problems. Classification basically categorizes, and regression maps to a number. Sometimes things may look like a number, but they're actually classes. And sometimes we use classes when actually regression might have been a better way of thinking about it, because the numbers are embedded in a metric space, so there's a concept of distance between them, whereas in the set of labels everything is equidistant from each other, so you don't look at it that way. So when it comes to inferencing, there is a whole bunch of things that you can apply, and already sort of most of you are kind of familiar with these things. So there is naive Bayes, which works extremely well as a first cut, despite a lot of simplifying assumptions. Linear classifiers and classifiers with nonlinear kernels we use all the time. Support vector machines, decision trees, multi-layer perceptrons, and deep neural networks. All of these things sort of currently exist and very robust tools, and we I'm sure you have seen them in various classes and all, but I'll sort of very briefly describe some of these things. The main thing to remember though is that the way normally we end up using these things is with these assumptions. That is, we make independent window based inferences there. When it comes to taking a whole trace and of observations and then making an inference, then you need methods which can keep track of that state, which can keep track of the whole chain of observations. So this is where recurrent neural networks that Vikrant had mentioned, LSTM is an example. But even in traditional machine learning, there are methods like hidden Markov chain and conditional random fields and things like that, which have that capability. And even without that, oftentimes a cleaning pass may be useful. So what you can do is you can look at the output of your classifier for each window, and then you can subject it to some simple filtering rule. Like, for example, if you were seeing running, sleeping, running, well, there's probably something wrong there. So you can do a cleaning pass over the inferences to, again, kind of smooth it out. So just something to keep in mind, that there are easy ways one can kind of deal with these things. Okay, so before we start processing the data with these classifiers and all, one of the first things you have to do is to clean them up, okay? And these sensors tend to be very noisy, make very sort of weird reports. Like, for example, I have this sort of chest belt which I use when I exercise on my home machine, and for some weird reason it always occasionally gives that my heart rate is like 210, 225, but it gives 1 or 2 readings and then it goes back to normal, which obviously is false, happens perhaps because of some contact reasons and stuff like that. But if I leave it in and use that for some inference making, then that would be kind of problematic. So one has to kind of clean this signal up. And this is where sort of understanding your sensor is very important. Lots of different reasons why sensors introduce uncertainty, but one has to kind of take into account. So one of the challenges that people currently struggle with is, how do you quantify uncertainty? How do you percolate or propagate uncertainty through your system? So, like, for example, if I were to again, many of you are doing this work where sort of you're taking these measurements and subjecting it to some classifier and reporting a result, and then you also report some uncertainty about it by looking at, for example, a softmax number from the neural network. What uncertainty do you think that softmax is capturing? So, like, when your neural network says label A with probability or whatever with 90% score and label B with 10% score, what is the what aspect of what uncertainty is that reporting?
Softmax returns probability of so if A is 0.9, it means that gesture A comes with probability of 90%.
No, it's saying that gesture it saw is gesture A with probability 90%. But what's the probability about it? Like, why is it Why is it giving a what is the reason behind it being a probabilistic thing? Huh?
The signal is
No.
the measurement unit itself.
Huh?
The measurement unit itself.
The measurement what?
Like a measurement unit, whatever is being used, like a physical sensor.
No.
Sensor medium.
No. It is really declaring an ambiguity in the decision making process. So like it's not the measurement noise, but a statement about the world, right? I mean, like for example, I don't know, like let's say, what would be a good example? If I'm trying to classify whether it is a sedan or a crossover or a SUV, well, there's some cases where it is genuinely ambiguous, right? I mean, some sedans look like crossovers and some crossovers look like sedans, okay? So it's really a statement about the labeling in the world, okay? Walking and jogging, these are ambiguous things, okay? So it's really reflecting that ambiguity, that in the training data, there were instances where was jogging, but it was perhaps walking for some other individual, right? So it's saying that the decision boundary is. On the other hand, my sensor input may be noisy or may have something, right? So that doesn't play into this thing, because it's basically saying this is the test input you gave me. I'm giving you my answer on that test input. But the test input having uncertainty is a different form of uncertainty, and that is what these things are, right? That if my microphone was messed up and it adds some screeching noise to it or something like that, right? I mean, that is, then it will take the screech as a valid test input and do it, even though it is an artifact of the sensor. So that's a different form of uncertainty which those softmax are not capturing, right? It is really an uncertainty about the input, and so we have to have some way of sort of propagating that forward. There is a third form of uncertainty which also exists, and that is uncertainty in the training data, in the model itself. So what I mean by that is, you take that training data and you train a model with different choices of hyperparameters, learning rates, stuff like that. You may have ended up with a different model, right? So the model itself represents an instance of a whole bunch of different models that could have been very validly learned on that data. So that's the third source of uncertainty. Uncertainty in the training data, uncertainty in the training procedure, uncertainty in the labels, and which kind of cause the ambiguity that we see in the softmax, and then finally uncertainty in the input itself, the test input itself, right? That the data are noisy and stuff like that. And our ability to understand all of these things is still not that great. There is one framework that people often use, is called Bayesian deep learning, and kind of the idea is that instead of thinking about one neural network, you think about that each parameter in the neural network is a distribution. So it's really what you have is a family of neural networks. So whenever you do test input, instead of doing it on a neural network, you are really subjecting it to a distribution of neural networks. So you can say, I will draw a random neural network out of the distribution and then report the result on it. That instance itself will give me some softmax, some confidence values and all. That's kind of a separate issue. So important to bear in mind that there are all these different sources. The one which we are talking about out here is the uncertainty in the test input, and also uncertainty in the training data, okay, because the training data is what is usually through the same sensors itself. So ways to mitigate some of these things. So first is a lot of effort goes into sort of cleaning up the signals right at the sensor. Transducers tend to be kind of noisy and all, so there's a lot of effort at the circuit level and all to kind of clean things up, average them out, calibrate them, stuff like that. All of that happens. I'm sure you would have seen these things. Even simple stuff like switches and all are subjected to debouncing circuits and stuff like that. The more Another thing which is done is sensor calibration. And what sensor calibration deals with the fact is that the signal that you are getting and the signal that and how you are mapping it to the physical value of interest. There may be lack of calibration in it. So for example, if you have a sensor which is reporting your heart rate, then is it doing it correctly, or a weight sensor? And also usually sensors have some calibration procedure. Some sensors are pretty bad at when it comes to calibration. They require a lot of effort. Sometimes you have to have special procedures in place. Sometimes sensors have memory, so that over time they begin to drift and their calibration parameters change. So like for example, magnetic sensors which exist on our phones are notoriously subject to that. Okay, so over time they begin to saturate. So I'm sure you have, I don't know whether it exists on Android or not, but until not too long ago, Apple often used to have like move your phone in a 8 thing. Have anyone seen that? Like, I mean, yeah, right? I mean, move it in a particular way. That was an attempt to kind of recalibrate the compass, the magnetometer in the sensor. I think since then there are better procedures have emerged. They kind of take advantage of the fact that we move our phones around and all anyway during the day, so some of those things happen. Precise calibration is also important for any sensor which has converts information which is easily impacted, like level of radio signal strength, these kind of things. So calibration becomes quite important there. So calibration, there are really this question of mapping that physical variable into mapping the measurement into the physical variable, and then also things there may be other terms in this thing which may be affected by like the surrounding temperature and battery voltage and stuff like that and all. So there are a couple of ways you can calibrate. One way to calibrate is to compare the output of your sensor against an output of a good sensor, often called as a gold standard. So there is some reference standard sensor and we compare against that. And the other one is that we have some reference input. There is a signal generator which generates a precise signal, and we subject our sensor to that and look at its output, and then we calibrate against it. So these are kind of couple of approaches that one can use. Oftentimes sensors come built in with a reference signal generator, and then they kind of make use of that. Question for you: why don't, like when you guys are using all these variables and stuff like that and all, why don't we worry about calibration?
So already factory calibrated.
Okay, so one possibility is factory calibrated, but did you check?
Yeah.
You did, and they are good?
There's a code on that and that's it.
Okay. What if it was not calibrated? Then what would happen? How would you cope with it?
Map the sensor values to that.
Okay, so one is you can do a calibration procedure. The other is you can take a large ensemble of those sensors and then train your model over readings from those, right? So don't just train on one or a small number of instances, but really buy multiple batches on different dates and stuff like that, so that you have a diversity of manufactured pieces, and then you train the model with data from those. Otherwise, your model may not generalize because the device may have differences. Sensors tend to have very unique fingerprints. So there are several papers have emerged in recent years which show that if I were to give you the trace from a phone, the IMU trace, for example, from a phone, then you can sort of link it back to the phone. So like, I mean, let's say you have the trace from my phone from last year, and I share, and then I publish some data anonymously today, you would be able to link it back to that, because perturbations in the signals exist which are very unique, and some of them have to do with calibration parameters, and some of them have to do with the noise parameters. Likewise, cameras. So when you have a totally dark image in a camera, like take the camera and just take it in a dark room, then the picture you get is a very noisy, grainy picture. But the noise pattern in that is very unique to the particular camera, particular imager. Likewise, radios have unique fingerprints. So there are a lot of these papers which have emerged which kind of use this thing as a way to break privacy by kind of linking things back. So sensors, the sensor calibration is, or lack of it, can also be a little bit of privacy security implications. A third issue which you face is that everything you might try and all, and then in real world, all other things, there are all sort of other things which go bad. So there is often instances of like missing data. So these are actually real data traces from some real deployments in a group at UC they were doing, and you see kind of all these things like missing data pieces or like weird things happening and all. And the problem is when you have these things out in the wild at scale, you don't know what was happening. So you have to be kind of prepared for sometimes it's software, some network outage, just something. Maybe Android decided to kill your sensing app because it was consuming too much resources, or any number of things which can happen. So it's not just calibration, but these kind of issues. Sometimes also outages have other implications, like if there is a network outage, your sensor may still be collecting the data, but the timestamp on that data may become off because it's not able to time sync back. So then again, kind of you need some way of doing things. Rainwater falling on the camera of your car, kind of all these kind of examples, sort of. Okay, so after we have cleaned up the data, actually one other thing I wanted to say is the following, that both for sampling and for calibration and cleaning up the data, a lot of people now, we often use machine learning systems in that process. So basically, I presented those examples like when to collect the next sample. Well, there is a whole field called active sampling, and the idea in active sampling is that we use a machine learning model to predict when should I sample next. So I kind of I basically train on the data and kind of use that to kind of predict things out. And likewise, when it comes to missing data, these kind of things, there's a body of literature, again relatively recent, which basically is called sensor data imputation and missing data and whatever, filling in the missing data. So there are two versions of this problem. One version is that I give you this time series and there are gaps in it, and can you fill those gaps in? How do you think, can you think of some way to approach that problem? So the reason we might want to do it is because rest of my software chain assumes that I have good data. So instead of handing it data which have all these gaps, because then it will fail, so I need to fill it in, but how should I go around filling it in? That becomes a question. So can you think of some way of doing that I can fix it? Yeah.
I mean, if it's a periodic signal, you can make assumptions about what you're expecting based on like what's happening.
Yeah. So I mean, none of these things are periodic, but essentially it's a prediction problem, right? So what we are doing is, given the history, we want to predict. So I can train a model for that. I can collect good data, and just like currently you train models to make inferences, in this case the inference is what the next value is, right? So I can essentially learn an extrapolator, or actually even in this case I have both the past and the future, so I can look at both and then fill that in. Okay, so I can do a smart interpolation kind of thing out here. So that's the missing data problem with a single channel. Oftentimes what we have is multi-channel sensor data. So it could be that one sensor has a gap, but other sensors are not. So I can look at the neighboring channels. Like for example, let's say my gyroscope data got crashed or messed up. but I have the accelerometer data. Maybe I can use that to fill it in. And actually it turns out that if you think about it a little bit, we use inertial sensors with 9 degrees of freedom, right? I mean 9 channels, 3 accelerometer, 3 gyros, and 3 magnetometer. But we only have 6 degrees of freedom in our thing. So clearly we have redundancy there, right? Something can be computed from something. So it ought to be possible that if some channel is missing, I can fill it in with other channels. And that problem is called imputation. So when I'm imputing data in one channel by looking at the neighboring data. Again, deep learning methods are proving very effective on it. Back to my inertial question, which across these accelerometer, gyro, and magnetic, which one do you think I can predict from the other two? Huh? Say it again?
You predict the accelerometer over gyroscope.
No, the other way around. Other way around. You can get the rotational velocity from that together with the magnetic thing. So accelerometer plus magnetic can give you a gyro. But we still use a gyro because it would be a very noisy process otherwise. So that's why we do it. Okay. So even for these problems like calibration and missing sensor data and stuff like that, deep learning and these kind of methods are proving immensely helpful. And the reason you, again, repair the signal is so that rest of the software chain doesn't get impacted. That's kind of the idea, okay, instead of going ahead and feeding it in. So for example, even when you are doing windowed inferencing and stuff like that, you might want to either repair the windows or repair the output of your classifier by treating it as a missing problem. Okay, finally, it's about making the inferences. So how do we go from sensor data to inference? Broadly speaking, we encounter two kind of sensors. Sensors that generate event reports, so which are basically reporting change in state of the system. Like, for example, every time the door opens, closes, maybe it sends out, or every time there's a motion, it sends out something. But it's not sending a repeated message, door is closed, 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 open, right? I mean, it's sending out events. So many sensors are naturally like that. Deep down, what is really happening is that they may be still continuously sampling, but then some simple processor right at the sensor kind of takes care of converting it into an event report. And then there are sensors which are sending data at a lower level, namely they're literally sending that periodically sampled time series. What we are interested in is we want to make an inference about the state of the world. And one way of doing this thing is that given the measurement, I would apply an inverse physics model and then get to the state. That works only for very simple things, like I can convert voltage to temperature or stuff like that. Okay, but for more complicated things, that's kind of out of the question. And the other approach is really we learn some sort of a data-driven model and then train it and then apply that. So what we have begun to see is that for more complicated sensor data types, it's a second approach which is really kind of has excelled. So I think applying physics-based approaches to very complicated sensor data type haven't quite succeeded, right? So if you look at like computer vision and all, the classical computer vision was all in terms of thinking about rays and lighting and textures and stuff like that and all, and a lot of effort was based on like how the image gets generated, and then therefore how can we go back to what the object were, and but in recent decade or so, I mean, those methods have just dropped dead basically. So typically ML algorithms do not process the raw sensor data, although increasingly it is beginning to happen. So so when I say typically, because we kind of operate at the level of features, but what has also begun to happen is that people are showing that kind of doing these systems end to end, raw data all the way to the inference in one shot, works better in many cases. So like for example, when it came to things like, let's say, speech recognition, very common was that we'll take the sound signal and then we'd extract certain features from that, MFCC coefficients as they were called, and then feed them in. But again, a lot of work showing that you feed the raw signal and go through it. With images, we are pretty used to at this stage of just feeding the raw image, the pixel values directly to it, and not extract, let's say, edges and stuff like that of that. So end to end is becoming more popular, but still, I would say probably the norm still is, by and large, extract features. So those features are designed by humans, and selecting them itself is kind of a difficult task, require a lot of effort and all. One way is to really have kind of a big list of type of features that people generally use, and then see which one of them are working well through some systematic procedures, and then kind of go with that. So it's a combination of expert intuition, historical knowledge of what has worked or what hasn't worked, and then kind of applying it to your context and all. So broad categories of events that might exist. For example, for event sequences, time of occurrence. So like it could be time of day of week. So you can think of these features also, right? So instead of so you have events with a timestamp. So the raw event stream will simply look like that timestamp, except that that timestamp doesn't really have the semantic knowledge. Whereas we know that we are dealing with human activities and all. So perhaps, and our human world follows patterns like holidays and workday and weekday distinction and work hours and off hours and all. So going from this raw information to something which carries some semantic sort of utility for our application is tremendously useful. What's going on out here? When I go from timestamp, the time of a timestamp, the raw timestamp, to this, am I adding information to it, or is it the same information? What's going on out here? So this process of going from kind of the raw timestamp to these kind of features, is it throwing away information? Is it adding information? What is going on? It's adding. Yeah, there is some human knowledge which is being added to it, right? Knowledge about that certain things take place on certain days of the week, right? All those kind of things are coming in. So while there is certainly a reduction also, in the sense I cannot go back from this, but there is also addition of information out here, and that's extremely valuable, right? That we are bringing side knowledge to this thing. Okay, so on the other hand, there are other things where we are not really adding, like the sequence duration, like what was the length? I mean, this is really just dependent upon this, but like time of day, day of week, these are information which have some implied, or other things could be like location, like is it, what type of location it is it a home? Okay, so that suddenly adds additional information to it. Another very common type of feature which is used is something which is derived from document processing. So in document processing, number of years ago, kind of it became very common to sort of map documents to vectors. And one very common way of mapping documents to vectors was frequencies of words. So essentially, we'll take a document and then say that look how many times the word the occurred, how many times the word Los Angeles occurred, and so on and so forth. So we'll kind of just do map and then think of the document as that. So that model was called bag of words, and they'll do some further normalization and all, but basically you'll take a work with that, and then similarity of documents and all sort of other things really became operations on that vector. Same thing out here, that when it comes to these kind of sensors, I can think of events with associated frequencies. So what I can do is I can look at a window of time and then different sensors and their firing frequencies. I can say how many times they fired. So like you might imagine that different activities may result in a different vector in terms of these. So like for example, I don't know, like let's say when I'm using the toilet versus when I'm cooking in the kitchen or doing cleaning or stuff like that, if I were to look at the corresponding vectors, they'll probably have very distinct flavor to it. So I can go from these time series of events and all to kind of this more compact kind of vectorized representation. So so this notion of taking this messy sensor data and mapping it to a vector and then processing it has caught on to the extent that even in neural nets and all, we kind of think along those lines, that the role of the initial layers of neural nets is really to map my sensor data into a compact vector of some form. So like one or two groups are doing NLP projects and also there is this whole concept of word embedding in NLP. Is the same thing out here, that you can think of the sensor data kind of can get mapped into some vector representation of what is happening in the world space. In this case, it's though sort of simpler than that. And elapsed time since last event. So there are a bunch of these features that you might imagine, which are ways to convert events into kind of more statistical features over a time window. So like I can look at sort of various statistics and then also some other contextual information. Usually, since computing the features is a costly procedure, in fact, often in non-deep learning type settings, this may actually be the bulk of the computation that you are doing, so there are well-optimized libraries. It's very much kind of like classical signal processing. Many packages will supply you kind of with a big library. So I've kind of listed a whole bunch of them out here: temporal, spectral, these kind of things. So oftentimes with data sets, what you would see is that they will give you a data set and they would have already computed these features. And like there may be hundreds of such features. But you're not going to train a classifier on all those hundreds of features. You will, important task would be to kind of reduce it down to a more manageable set to see which one are more useful. So very loosely speaking, the approach that some of these systems take is the following. So let's say you have computed all these features and you have this, you're going to learn a fancy model on it, something which neural nets and all, let's say. And if you have large number of features, the training procedure would be very expensive. So the way we prune these things is we take a lower order model, maybe let's say a linear regression. And then on that linear regression, we see which of these features are most explanatory, the ones which have a high relevance to my output result. And then I retain those and I discard the rest. So there's kind of a search process which goes on during that time, but we identify those features which are more relevant. Features may be duplicative, so you also want to make sure that you are not over-representing things which are highly correlated. I've got two features which basically give me the same information. Then if you include both of them, then they are going to cause you trouble. Okay, so there's a whole list of these features and kind of one can start with this. Another aspect which one has to deal with is that oftentimes you have multiple sensors or multiple channels and you need to combine them somehow together. So there are very broadly three different approaches one can follow to this. So one approach, which is kind of relatively rarely used, but let's say I have a set of identical sensors, then I can literally fuse their readings. I can like just combine, average their readings. Like if I have 10 temperature sensors in the same place, I can think of my temperature as a summation over the two. So under some circumstances, you can kind of fuse the data. And maybe not average, maybe you might do weighted average or something smarter there. More common is feature fusion. So you take features from different sensors and then you concatenate them into a bigger feature vector and then you work off those. So in this case, what might be happening is that you're basically getting some information from each one of these, but then you are combining them into a single vector. And then finally, classifier fusion. What you do is you let each one of these sensors make an independent decision, like let's say on what the activity is, and then use some sort of a voting approach to kind of combine these things together. Generally speaking, so actually, which one do you think will do better? Data, feature, classifier, or what? Like what makes more sense? Last one, classifier fusion. Okay, this is one of those cases where the extreme is not the best. So the problem with classifier fusion is that some sensors just don't have sufficient information to make a reliable information, right? So you will have a very noisy sort of thing, result that you are going to be getting out of it. In a sense, so this is called hard decision and fusing the hard decision. So I'm forcing each sensor to reach a hard decision and then kind of just literally combining them. More generally, people like to use this intermediate one, which is soft decision making. Okay, so we are basically combining the results so that even if a sensor may provide some partial information, like maybe let's say I'm trying to recognize the individual, maybe a sensor can sense the height and the other one can sense the gait and the third one can sense something else, but combining them together, I will generally have a better sense. So feature fusion is what tends to get used, although in system-like settings, oftentimes it's a combination of the two. At a single node, you might do feature fusion or among neighboring nodes, but across different groups or different individuals, maybe you will do classifier fusion. So there's a whole area